Thank you. So our talk is again about effects handlers, but this time with names. So this is joint work with Ming sitting over there, and Kazuki sitting there, and Dan, who is probably watching on AirMeet. Okay. So effects handlers are a successful approach to expressing computational effects. One of the strengths of effect handlers is that we can easily program with different kinds of effects. For instance, if we wish to use read-only state and an exception, then we just need to wrap the computation around two handlers, one for reader and the other for exceptions. When effect handlers are extended with a name, we can further program with different instances of the same effect. As an example, if we want to maintain two read-only states, then we install two name handlers, H1 and H2, and then when we perform an operation call, we select one of those handlers. So by doing this, we can handle the first ask with the outer handler and the second ask with the inner handler. And such selection of handlers would be difficult to express if we use regular unnamed handlers. More specifically, we need to use a trick called effect masking to skip certain handlers. And this is inconvenient, and it is also non-scalable because we need to know what handlers are surrounding each operation call. So named effect handlers are indispensable from the user's perspective, and in this work, we explore the design and applications of named effect handlers. We show that using effect handlers with first-class names, we can build many interesting programs. And we also show that there are many different ways of designing such name handlers. In the rest of this talk, I will discuss the applications, type systems, and implementations of named handlers. Okay, so let's begin with applications. We will use the Koka programming language for all of our examples. Our first example is files. For this application, we define the file effect, which has a single operation called readLine. Here, the fun keyword is a unique feature of Koka. It means any interpretation of readLine will resume with the final result at tail position. By explicitly marking operations with fun, we can reduce continuation capture at runtime. Having defined the file effect, we next define a handling function for this effect. The file function here takes in a file name and an action that performs the file effect. Given these arguments, the function reads the content of the file using Koka's local mutable variable and file API. And then it evaluates the action under a named handler that interprets readLine as returning the first line of the file. Okay? And using this, we write a program that opens two files and concatenates their first lines. So here, we create two name handlers, F1 and F2, representing the two files. And then we put the handler names into a tuple and pass them to the catlines function. And note that we can do this because handler names are first class. If they were second class, we would not be able to put handler names into a tuple or pass them to a regular function. That's our first example. Our second example is first-class heap. For this example, we define two kinds of effects. One is the heap effect, which has an operation for creating a new reference cell. And the other one is the ref effect, which has operations for accessing and updating the value stored in a reference cell. We next define a handling function for each of these effects. For the ref effect, we use a named handler and implement the get and set operations using Koka's mutable variable. And for the heap effect, we use an unnamed handler and we interpret the creation of a new reference cell as handling the resumption using the ref handler. So here we are using the resumption as an action, which is not what we typically do with effect handlers. And now we write a program that creates two reference cells and accesses their values. So let me show you how it works step by step. So we begin by calling the make2 function under the heap handler. To create the first cell, we perform the new ref operation while pushing the context on the stack. And this operation call turns into a call to the ref function with the action argument being the resumption of the first cell. And this function call turns into an application of resume to the handler name R1 surrounded by the reference handler. And by expanding resume, we obtain a pair whose first element is a handler name. And now we move on to the second cell. We repeat the same process, and eventually we obtain a pair of two handler names. And after accessing their values, we finish the computation. So there are a lot of things going on here, but the point is that we can express dynamic generation of reference cells as dynamic creation of named handlers. And again, the program relies on the first class status of handler names. Okay, now we turn to our third example, which is a neural network. For this application, we define a layer effect representing the layers in a neural network. This effect has operations, get and set operations for weights and biases, and an operation called SGD, which updates weights and biases based on the gradient descent algorithm. And in the handling function layer, we use a named handler, which interprets get and set just as we do in the ref handler. And then we implement the SGD operation in the same way as the previous implementation that uses control operators. Okay, now we can build a neural network by creating a bunch of layer handlers and put their names in a list. So in the case here, we are creating a neural network consisting of one input layer, two hidden layers, and one output layer. And then we can perform learning tasks by supplying some training data. And as in the previous examples, we are using handler names as first-class values, more specifically as the elements of a list. Okay, so we've seen how named handlers are useful in practice. We next look at how we can design a sound type system for named handlers. In a language with effect handlers, type soundness relies on effect safety. That is, if a program is judged pure, then it cannot get stuck by performing an operation that has no matching handler. In a language with named handlers, the association between operations and handlers is determined by names, so we need to make sure that every operation that will be performed at runtime will have a corresponding handler with a specific name. However, this invariant can easily be broken. As an example, let's consider the program here. The program installs two named handlers for the reader effect and creates a function that performs the ask operation on the name h1. This function becomes the return value of the inner handler, which in turn becomes the return value of the outer handler. Now the name h1 has escaped its scope. So when we call this function, we will get a runtime error saying that there is no handler with name h1. So how can we reject programs like this? There exist several solutions to this name escaping problem proposed by Biernacki et al. And Zhang and Meyers. Their idea is twofold. First, they treat handler names as second-class values and restrict their use at the level of syntax. And secondly, they augment the type system with an additional context for storing names and some mechanism similar to dependent or region typing. This guarantees that handler names can never escape. But is this the only way to obtain this guarantee? Our answer is no. We show that it is possible to make handler names as first-class values while maintaining type soundness. And the idea is to give handlers as a rank 2 type, similar to Haskell's runst. This approach not only prevents handler names from escaping, but also allows us to seamlessly extend an existing effect handler language without adding any new constructs. Now the question is, how do we incorporate rank 2 types? Our solution is to combine named handlers with a special kind of effects, which we call scoped effects. Scoped effects differ from regular effects in that their effects label is associated with a scope variable. For example, the vector effect here, which represents a locally isolated state, has a scope variable S in its effect label. And when we define a handler for a scoped effect, we require the action to be polymorphic over the scope variable. And this guarantees that any resource made available by a handler will never escape the handler scope. In the particular case here, we know that we will never access a vector using an index returned from some other vector because the polymorphism makes it impossible for the index to escape. So we are going to use scoped effects, so combine scoped effects and named handlers to prevent handler names from escaping. And since these concepts are completely orthogonal, there are many different ways of combining the two concepts. So let's use one of the combinations to implement a safe version of our file example. And here we define the file effect as a scoped effect by attaching a scope variable to the effect label. And this scope variable appears in the type of the file handler name. And in the type of the action, we universally quantify over this variable. And now we know that we will never access a file outside of its handler. That's one way of combining named handlers and scope effect. Let's use a different combination to implement a safe version of our heap example. So here, we are defining the heap effect as a scoped effect and the ref effect under the heap effect. And this brings the scope variable to the type of the ref handler name. And in the type of the action for the heap handler, we universally quantify over this scope variable. And this allows us to dynamically create multiple references under a single heap. And it also guarantees that we will never access a reference outside of the heap. So thanks to the rank 2 type, we can prove type soundness for both combinations of named handlers and scoped effects. Following the traditional syntactic approach, we prove the preservation and progress lemmas for top-level programs. So we've got two sound type systems for named handlers. Now you may wonder, which type system is better? We think that there's no clear answer to this question. Each combination has its own pros and cons. The first combination of named handlers and scope effects is relatively simple, but it cannot express dynamic generation of handlers. The second combination can fully express our heap example, but it is theoretically more complicated. And other than these combinations, we also have named and unscoped handlers, which are unsafe but easy to use. From this comparison, we can conclude that there is no best design of named handlers. So the language implementer must choose between different options depending on what they prioritize. So in Koka, we implemented all the variations of named handlers. So let me briefly talk about the implementation. In Koka, effects handlers are evaluated under the evidence passing semantics. The semantics turns a handler into a control prompt tagged by a unique marker M. When going inside the prompt, the semantics creates a pair of a marker and a handler, which we call an evidence, and implicitly passes this evidence down to the body of the prompt. And when there is an operation call, the semantics extracts the corresponding handler by looking up a vector of evidences representing the handlers surrounding that operation call. So it has been shown that using the evidence passing semantics, we can improve performance by reducing handler search and continuation capture. And if we carefully look at these rules, we find that evidences play a similar role to handler names. Observe that the semantics turns an operation performing into an yield operator, which directly yields to a prompt that is tagged by a specific marker instead of the innermost control prompt. And this means Koka treats unnamed handlers already like named handlers. For this reason, it was very straightforward to support named handlers in Koka. The main change is that instead of looking up the evidence vector, we use the explicit handler names supplied by the programmer. As mentioned before, in Koka we support both combinations of named handlers and scoped effects. We also have named and unscoped handlers and unnamed and scoped effects. Having all these variations is useful because the programmer can pick one that suits their application. Indeed, in our 3 practical applications mentioned before, we all use different variations of named handlers. And one thing to note here is that for the unscoped variation, Koka inserts an exception effect because the program may raise a runtime error due to the absence of matching handlers. All right, in conclusion, effects handlers with first-class names are very useful, and there are many ways to design such named handlers. Our Koka implementation is available online, and we invite you to try out different variations of named handlers. Thank you.
Yeah, thank you for the talk. Are there questions? There's one on the left.
Yeah, nice talk, nice work.
Thank you.
Your named handlers and named effects reminds me a lot of dynamic instances in F. So I'm wondering, how does it relate? Can I think of this as a type system for dynamic instances, or are they fundamentally different?
I think named handlers are essentially the same as effect instances in F. Yes.
More questions? There's one.
Yeah, thanks for interesting talk. So I'm curious about you can provide CPS interpretations for the named effect handlers. Yeah, because sometimes CPS interpretation can provide a guideline to design a rich type system, like an answer type modification type system.
Yes. So I think it is possible to define a CPS translation for our calculus. I'm not sure how hard it would be to prove the type preservation because we have all this rank 2 types kind of stuff. But yeah, it would be an interesting future work.
Yeah, thanks.
Thank you.
Sam?
There seem to be some clear similarities between what was going on in this talk and in the previous talk. I wonder if you have any thoughts on the relationship, for instance, between the evidence passing style and the capability oriented architecture, and the relationship between named handlers and this notion of lexically scoped handlers.
Yeah, our handlers are just the normal dynamic handlers, right? I'm not sure how this work is related. Nini, do you have any thoughts?
Yeah, I guess.
Microphone.
Can you get the microphone, please? Can you? Otherwise, our external visitors.
Test. Okay.
Thank you.
I think in some sense our handlers are still like the regular handlers. It's like dynamically scoped. And I guess they give like a different semantics, like scope-based semantics to capability pathing based effect handlers. But also, I won't be surprised if the capability pathing based handlers can actually be elaborated into our system, because in essence, like capabilities can be expressed as like named handlers. You ask from the context, but that would be like an interesting question.
Yeah, I have a brief follow-on. So I was thinking that you were asking, so the second class stuff that was shown in the previous talk, isn't that really the same as the rank 2 restriction in this scoped handlers? I mean, the effect you get through typing here is the same as is imposed with the second class values, as far as I think?
I'm not sure.
Maybe we should ask the previous speaker. Is he still around? Do you want to comment?
Yeah.
Okay, so I think that the major difference would be that in the system that I was presenting, we track, we don't have effect rows, right? So just the sort of information that we track is ultimately different. We track sets of capabilities that are closed over, and that's in some sense a natural information to track. Right? Whereas this work starts from having an effect row and then adds naming handlers to that. So in some senses, the expressivity is similar, but the types will differ.
I mean, so all I was saying is it looks like the mechanism has the same effect. It's too many uses of effect. Yeah, I mean, the rank 2 encapsulation seems to have the same result as the second class restriction that you've got.
Right. I mean, rank 2 is one way to establish scoping of some values.
Okay. Any other questions?
We have a question in the Q&A from Ahad Kamar. In F with dynamic instances, one needs a value restriction. Do you know if named handlers require a similar value restriction?
We haven't thought about that. Do we? We have polymorphism. It's basically a system F like calculus with effect handlers, right? And
Is there another question up there? That's the last one. Then we need to
Yeah,
move
if
on.
there's no other question, is just a follow-up on what you were saying. I think that the rank 2 encoding is actually quite different from second-class values because it's more flexible. It relies on parametric polymorphism, and you can handle the values that are inside the rank 2 function arbitrarily, right? But in second-class values, they can only go up the stack. They cannot go down, even within the same scope, right? So it's kind of an approximation. The second-class values restrict the operations you can do with the value. So it approximates the rank 2 encoding, I think.
As far as I understand, but we can take it offline.
Yeah, sure.
Let's take it offline, I guess. It's not about the speakers. Well, thank you again.